Na qualidade de primeiro secretário da Academia Nacional de Medicina e em nome do presidente Jorge Alberto Costa e Silva, eu gostaria de convidar vocês para ter o privilégio de assistir à conferência do nosso convidado internacional, Robert Gale, que vai nos falar a respeito de lições de Chernobyl, se nós podemos sobreviver ao terrorismo nuclear. Eu gostaria de convidar o acadêmico Daniel Tabac para fazer a apresentação do nosso convidado internacional, que então fará a conferência de encerramento da sessão de hoje. O acadêmico Daniel Tabac.
Senhor secretário, senhores acadêmicos, convidados, eu gostaria de agradecer imensamente a oportunidade da academia de trazer o professor Gale para nos dirigir uma palestra muito interessante, da qual ele teve a oportunidade de participar em várias ocasiões, diante da sua formação. Eu tenho o prazer de, na verdade, dizer que nós nos conhecemos há mais de 30 anos. O professor Gale me entrevistou durante a minha formação e minha aplicação para o meu fellowship na UCLA. Eu, enfim, fui treinado em uma outra universidade, mas nós mantivemos essa nossa amizade durante muitos anos. Ele é um dos principais nomes na hematologia e no transplante de medula internacional, e diante da situação que se estabeleceu em Chernobyl em 1986, durante o acidente nuclear, onde as vítimas foram, de fato, muitas delas tratadas com transplante de medula óssea, a sua experiência ganhou, enfim, uma grande notoriedade. Ele participou nos acidentes de Fukushima e também, a meu convite, veio aqui para o Brasil e nos ajudou na condução da vítima dos acidentados do Césio. Ele vem ao Brasil regularmente, ele é um grande amigo aqui da população e dos hematologistas no Brasil, e é um prazer enorme poder introduzi-lo aqui, e eu tenho certeza que nós vamos desfrutar de uma palestra muito interessante. So, Bob, thank you very much for joining us. I'm going to put in your slides, and appreciate for your time and being here, and I think we're going to enjoy very much your presentation. Thanks for being here.
Obrigado, acadêmico Daniel Tabac. Vamos ouvir o professor Robert Gale falando sobre o maior acidente nuclear da história, Chernobyl.
Obrigado. I was going to say boa tarde, but I'm going to say boa noite, because it's getting late. And I want to thank the Academy for inviting me, and for Professor Tabac for arranging this. So I'm going to talk about nuclear accidents, nuclear energy, nuclear terrorism, and nuclear war, lessons from Chernobyl, Goiânia, and Fukushima. The reason I'm giving this to a medical academy is because I think that physicians have a special responsibility in society on the issues we're going to discuss. We're highly respected members of society, and we have to use our influence. So we're going to talk about radiation. There are two kinds of radiation. There are ionizing radiations and non-ionizing radiations, and we're going to focus on ionizing radiations, which are radiations which have the sufficient energy to change biological molecules. And we can sort of divide them into particles like neutrons and alpha particles, or beta particles or electrons, and in electromagnetic waves. And if you look at this spectrum of electromagnetic, so if we look at this spectrum, let's see, Daniel, where is the pointer here? That's the pointer. I see. Okay, very good. Sorry. Well, I mean, we have a lot of non-ionizing radiation your microwave oven and things like that. These have very long wavelengths. And then we have ionizing radiations like gamma rays that have extremely short wavelengths. Now the average person in Brazil is exposed to about 6.2 millisieverts of radiation every year, or about 800 millisieverts, or a half a sievert. What exactly does that mean? Yeah, that's all right. It's not going.
Yeah.
Let's see. What do you think is? Okay, so what does that mean? Holy cow, what is a millisievert? Am I going to die? Should I wear a steel helmet and lead underwear? Let's see if it'll work. Okay, fine. So this is a complicated slide, but I'll just point out to you that 1/2 of our radiation comes from natural sources, and the other half of our radiation comes from doctors, physicians doing radiological or nuclear studies. So as physicians, we contribute 1/2 of the population's radiation exposure. Now, but not everyone that is exposed to this average. Let's say you're going to take a holiday trip to Guayapari. Sounds like a nice idea. Lovely beach in Guayapari. But Guayapari, for geological reasons, has extremely high levels of radiation. And you can see that this is the amount of microsieverts per hour, and this is the amount of millisieverts per year. Well, what does that mean? Well, if you live in Los Angeles, you can see that you get 400 times less radiation than if you were to be in Guayapari. And over the course of a year, you would get 400 times less. So if you go to Guayapari and spend a year there on the beach, you're going to get 400 times more radiation than I would get in Los Angeles. Now, we need some other things to compare this to. So for example, the chest x-ray. So a chest x-ray is about 0.1 millisieverts. So a year in Guayapari is like 11,500 chest x-rays, or it's like 40 abdominal CT scans. So all of us get different radiation exposures depending on where we live and what we do and things like that. Now, if we look at our lifetime background radiation dose, living in Los Angeles, I would get this amount, 240 millisieverts if I lived 80 years. But if I lived in Guayapari, I would get 400,000. And that's equivalent to 4 million chest x-rays or 13,000 CT scans. Now, I think many of you may have been to New York, and you will have seen Grand Central Terminal with this famous clock tower in the middle. And if you stand there, you know, the walls and the floor are made of marble. Now, marble is a natural compound that contains uranium and thorium and things like that. So if you stand in Grand Central Station near that clock, you will be exposed to more radiation than we allow in a nuclear power facility. Now, of course, you're not living in Grand Central Station, but just standing there, you're exposed to a lot of radiation from marble and from thorium. Now, what if you fly on LATAM? Well, do you get radiation flying? Yeah. So the average dose flying from Los Angeles to New York is about 0.35 millisieverts. The average dose of cosmic radiation that we get every year is about 0.33 millisieverts. And as I mentioned to you, you can compare that to a chest x-ray. So when you fly, of course, you're closer to the sun, and the duration of your flight and the altitude of your flight and your distance from the equator will all affect how much radiation you're exposed to. And if you go through these scans, many people at the airport are afraid to go through these scans. But if you have one of those scans that people are afraid of, it's exactly the same radiation dose as flying at 12,000 meters for 2 minutes, or waiting in the security line for 42 minutes. So if you're afraid of radiation, don't worry about the scanner at the airport, just don't fly. Now, I want to talk about the biological effects of radiation. And as you all know, radiation damages DNA, and here are a bunch of abnormal chromosomes, like translocations, or a dicentric chromosome, or a chromosome fragment, that are caused by exposure of DNA to ionizing radiations. And if you put a gray or a sievert of radiation through a biological system, you get all of these abnormalities: single-stranded DNA breaks, damaged bases, double-stranded breaks, and protein DNA crosslinks. And you can actually visualize this. This is the nucleus of a cell, and each one of these is the track of a uranium ion. And wherever you see these colors, it means the DNA has been damaged. So we can actually visualize this. And, I'm a hematologist, so one of the target organs of radiation is, of course, the bone marrow. This is a normal bone marrow for those that are not hematologists. And this is what it looks like if you expose a human to a high dose of radiation. Okay, so let's move to nuclear and radiation accidents. And I'm trying to go a little bit quickly because of the time. These are a number of accidents that I've been involved with. Chernobyl, Goiânia, another accident in Belarus, another accident in Japan, Fukushima, and then of course we have the atomic bomb explosions. I'm not going to cover all of these, but this is a picture of the Chernobyl nuclear power facility in 1985 before the accident. And I'll just point out the reactors, 4 reactors, and a turbo generating hall, and this cooling pond here. And okay, so in April of 1986, there was an accident and the 4th reactor exploded, and all of this is radioactive material on the ground. And this is a picture from Landsat. That's one of our spy satellites over the Soviet Union. And here's that pond, and here is the burning reactor and the radioactive plume. And of course, we had to evacuate about 120,000 people. These are people from Pripyat getting into buses to be evacuated. Now we can move to the Goiânia accident in 1987. And this is a radiotherapy device that was abandoned in a clinic and that was stolen by some people. And I think everyone here is aware of the contamination and mitigation strategies that were needed. Now here's Fukushima in 2010. It's actually quite like the Chernobyl situation here. Here are the 4 reactors and the turbo generating hall. This is the Sea of Japan. And you may have seen this on the television. This is an explosion of one of the reactor complexes. This is not a nuclear explosion. This is a hydrogen gas explosion, but it destroys the building, destroys the containment. And this is a flyby we did in a helicopter. You can see the destroyed reactor building. And here's another view of the destruction of the containment. And so we go into these kind of situations and we try to measure and estimate radiation levels and decide whether we need to evacuate people. This is our reconstruction of the radiation levels. Here's the plant, and here are these very, very high radiation levels tapering off. Tokyo is around here. And again, we had to evacuate more than 100,000 people after this accident. Now, people often ask me, how do Chernobyl and Fukushima compare? And I'll just quickly show you two pictures. This is the Chernobyl accident, and the red is high levels of radiation. And you can see that this radiation has spread all over Europe, in North Africa, and up into Scandinavia. And you can compare the intensity to the Fukushima accident, and you can see that it's much, much less, because most of the radiation was deposited into the Pacific Ocean. Now, when we have a radiation accident, we have different kinds of effects. Here's when the accident occurs, but these effects last for 80 or more years. So we have some very acute effects, immediate. We have some effects that occur over time, and these are deterministic effects. That means that for a certain dose of radiation, everyone is exposed to that dose of radiation, has the same effect. Cataracts, bone marrow failure, things like that. But over the long term, we have stochastic effects. And that means that the effects are dependent on the dose, but not everyone at the same dose has the same effect. And so I'm going to focus on these stochastic effects because I think that that's what most of you are interested in. Because these stochastic effects are cancer and birth defects and genetic abnormalities. And the one that people are most afraid of is cancer. And we know from the atomic bomb survivors and many other studies that if you increase the radiation dose, you will increase the risk of getting cancer. So there's a linear or a linear quadratic relationship between the dose of radiation and the chance someone will get cancer. Now, I don't know how many of you are aware that all of us have a very high risk of getting cancer in our lifetime. If you're a male, your chance of getting cancer in your lifetime is 43%. And if you're a female, it's about 39%. So almost 1 in every 2 of us in the room is going to develop cancer in our lifetime. Now, if we look at males whose baseline risk is 43%, and we expose them to more and more radiation, you can see that the risk goes up, but it goes up very, very little. For example, 100 millisieverts is a lot of radiation. It's the average survivor of the atomic bombs received 200 millisieverts. So this is half of an atomic bomb survivor's dose, but the risk of cancer only goes up 1%. So there's a definite risk, but it's modest. Now, we use these data to estimate what happened after the Chernobyl accident, and we're looking at the number of cancers that would occur in 80 years. So we have about 7,000 cases of thyroid cancer in young children. Only 10 of these cases were fatal, but that's a clear, these are children, 7,000 children with thyroid cancer is a huge, huge number. Now the other cancers, over 80 years, we expect to be in this range, 11 to 25,000. But the people in Europe, including the former Soviet states, during the same period, during the same 80 years, they will develop 200 million cases of cancer. And so it's very, very difficult or almost impossible that we could detect these cancers mixed into these 200 million. So our conclusions so far about Chernobyl, despite what you may have read in the newspaper or despite what you may have seen in the HBO television series, our conclusion that there's a marked increase in thyroid cancers, that's clear. There are very few, if any, leukemias, maybe a few cases of chronic lymphocytic leukemia. There's no convincing increase in other cancers, possibly a little increase in breast cancer. There are absolutely no birth defects and no genetic abnormalities. So all these things you read about thousands of cases of cancer and so forth, birth defects, children with, extra limbs or two heads or things, these are simply wrong. They're simply not correct. Now, we've done similar calculations for the Fukushima accident, again, over 80 years. You can see that we really don't expect many, maybe none, no cases of thyroid cancer. Other cancers could be 0 or as many as 1,500. But again, in Japan, about 20 million cases would occur in these 80 years, and we would have no ability to detect it. So again, if you read or see claims that there's a huge increase in cancer, it's simply not true. So our conclusions about Fukushima, there are few, if any, thyroid cancers, few, if any, leukemias, few, if any, other cancers, no birth defects, and no genetic abnormalities. Now, we can kind of express cancer risk like a thermometer. Being in the red area is bad. Being in the blue area is good. And we usually say in public health that a risk in 1 in 10,000 is a negligible risk. Now, I said that our baseline risk of getting cancer was roughly 50%, 1 in 2. If you're a smoker, of course, you have a higher risk. And if you do an abdominal CT scan, you are down in this range. It's not negligible, but it's very far away from our baseline risk. And if we put these nuclear accidents on the same thermometer, you can see that they are not negligible, but they are much less, for example, than an abdominal CT scan. Okay, so now I want to shift to nuclear energy. And this is sort of the United States' use of energy. So we get most of our energy from hydrocarbons. We get about 20% from nuclear, and then all these other things, solar, hydroelectric, etc., are important, but they make a very small contribution. So we're relying on hydrocarbons and nuclear. Now, there's a problem with hydrocarbons or fossil fuels because we have deaths from mining and transporting and burning coal. We have global warming to deal with. We fight wars over oil, the Persian Gulf War. And the cost is enormous, about $400 billion a year. Now, this may surprise you, I think it will surprise you, that we want to see how much radiation is released when you make 1,000 megawatts of electricity. So we're holding the amount of electricity constant, and we're looking at what happens if you burn coal or if you use nuclear energy. And you can see that when you burn coal, coal comes from the earth, and it has a lot of radioactive materials in it, thorium and radium and uranium. So when you burn coal, you release radiation to the atmosphere. And to make the same 1,000 megawatts of electricity, you will get exposed to 100 times more radiation from coal than you will from a nuclear power facility. So people, are afraid of living near a nuclear power facility, but actually they should be afraid of living near a coal burning facility. That's much more dangerous. Now, if we look at deaths per terawatt of electricity generated, we have deaths from accidents and we have deaths from air pollution. And then we have coal and gas and oil and nuclear. So we can compare these. And if you look here, I'm going to compare coal and nuclear. You can see that the number of deaths from accidents from coal is 7 times higher than from nuclear. Because you have to mine coal, you have to transport coal, you have to burn coal. And several thousand people die every year from those activities, whereas nuclear accidents are rather rare. So in terms of losing lives from accidents, coal is much worse than nuclear. Now, what about air pollution? Deaths from air pollution, chronic obstructive pulmonary disease, asthma. So you can see that coal, to produce the same terawatt, kills 500 times more people than nuclear. So again, coal is a very dangerous energy source. Now, should we stop? People are very concerned, and should we stop using nuclear energy globally? Well, Japan stopped using nuclear energy after the Fukushima accident and started using coal and oil. And you can see that their carbon output, the amount of carbon they deposit in the atmosphere that contributes to global warming, increased enormously. So that's the price you pay for not using nuclear energy. Now, if we continue using coal and oil the way we're currently doing, if we had a major intervention, which we don't have, if we did everything correctly, there would be a 2 Celsius rise in global temperature in 2050. On our current course, which is the most likely course, it's only 30 years from now. It's not 100 years from now. It's only 30 years. So that brings us to nuclear energy, which is the only way for us to solve the global warming problem on the near term. But we need to have some fixes. What do we need for nuclear energy to advance? Well, we need safer reactors. We need safer nuclear fuel storage. We need cheaper reactors, and we need better safety standards. So this is Santos Dumont. You know him better than I. And I think we're looking across. If you look out the window here, his airfield is just across. And, whoops, Danielle, let's see. Yeah, so this was his flying machine. And this is a modern American fighter jet. So we have to move from the very old reactor designs that we have previously used to modern designs. So this is just one example of a modern reactor. Much, much different, much more advanced, much safer than our current reactors. And we need these small modular units. The reactor is here. We need to be able to move these things around and put them together to make it more safer and cheaper to produce electricity from nuclear energy. And then we have to deal with this issue of the spent nuclear fuel, and there are solutions, like reprocessing. If you reprocess the spent uranium, you can salvage about 95% and reuse it, or 97%, and you can be left with only 3% of radioactive wastes. So there are solutions that countries are simply not using. Okay, so the next topic is nuclear terrorism, and physicians play an important role here. Now, I'm going to abbreviate this in the interest of time, but I'll just point you to an article that we published recently in the New England Journal of Medicine if you want more information. But nuclear terrorism is not a theoretical problem. These are thefts and sabotage of nuclear materials that have occurred so far. So there have been 152 episodes where a kilogram or less of a radioactive material has been stolen. There have been 24 thefts of more than a kilogram, and there's been 45 episodes of sabotage. So this is actually happening. Now, we have different kinds of nuclear terrorism devices. Just exploded in the middle of Rio, and then you have a radiation crisis. You can also just steal this radioactive material and disperse it in a plane. Just cover the city of Rio, fly over Rio with radioactive material. I mean, you'll have a riot in Rio when it gets into the news, it gets on the radio. Now you can also steal, like the people in Guyana, you can steal a radioactive device and put it on a train. And then we call this a radiation emitting device. So that's another way to have a nuclear terrorism. And then of course you can steal a nuclear weapon. We call that an improvised nuclear device. And this just shows you the range of damage that would occur from improvised nuclear devices of different size. And let's just compare this. So here's a radiation emitting device, here's a radiation dispersion device, and here's an improvised nuclear device. And these are the areas that they would damage, and here's what a nuclear weapon would do, a 10-kiloton nuclear weapon. So they're not as damaging as a nuclear weapon, but they can cause widespread damage. So just like in medicine, we want to prevent disease. We don't want to treat disease, we want to prevent disease. And the same thing goes for nuclear terrorism. We want to prevent nuclear terrorism. We don't want to deal with it. But we have to hope for the best and prepare for the worst. Now this is Helmut von Moltke. So we make plans, but von Moltke, who was a Prussian military officer, said, all the plans, no plan survives first contact with the enemy. Namely, regardless of the plans we make, in these crises, we always have to improvise on the plan. We can't count on the plan working. Okay, my final topic is nuclear war. Now, you know, this all started with the atomic bomb explosions in 1945 in Hiroshima and Nagasaki. And this is the amount of energy in megatons of TNT. Here's the Hiroshima bomb. Now, a modern atomic bomb, a 1 megaton bomb, has this amount of energy. You can just compare these. So the average weapon is 10,000 times more powerful than the bomb that was dropped on Hiroshima. And if we look at a hydrogen bomb, you can see it's 30,000 times more powerful. This is each weapon is either 10 or 30,000 times more powerful than the bomb that was dropped in Hiroshima. And this is the bomb that was dropped on Hiroshima. It's called Little Boy. This is a picture of it. It weighed 5 tons. It had 80 kilos of U-235, but the actual amount of matter that was converted into energy was only 700 milligrams. And that's what it did. That's Hiroshima just after the bomb. So you can imagine the power of these weapons. They caused 120,000 deaths. 90,000 were immediate and 30,000 were delayed. Now, I just want to point out how these weapons kill people. It's not what you think. Say a nuclear weapon, you think, well, radiation must be killing people. But that's not the case. The blast itself, because of the tremendous power of these weapons, this is the atomic bomb in Hiroshima. The blast, half of the deaths were caused by the blast. And another 30% were caused by the superfires. This is more than 100,000 degrees Celsius when one of these bombs explodes. And you do get deaths from radiation, but they are small compared to the thermal and percussive force of these weapons. Now, this just shows you the dispersion of nuclear weapons in the world. The major players, of course, are the United States and the Soviet Union. But there are a number of other countries that have nuclear weapons. Now, I'm going to just tell you some good news and some bad news. This is the American nuclear stockpile. And you can see that going from 1962 to 2017, we have decreased our nuclear stockpile very substantially. And it's been decreased because of a number of these treaties. You may have heard of START 1 and START 2 and New START. These are all treaties between the United States and either the Soviet Union or Russia. So that allowed us and the Russians to decrease our nuclear arsenals. But we have a number of wild cards around the world that have nuclear weapons. I mean, here's one of them in North Korea, and another one in Iran. So the fact that the United States and Russia have decreased their nuclear stockpiles does not mean that the risk of a nuclear war is over. And I'll just show you something that was in the news about 6 weeks ago. This is, and this reflects the fact that now the United States and the Russians are developing a new generation of nuclear weapons. This is what NATO calls Skyfall. This is a Russian cruise missile that is not powered by the normal rocket propellant, but this is powered by a nuclear reactor. So this cruise missile could stay, just like a nuclear submarine can stay undersea indefinitely. This cruise missile could stay in the atmosphere indefinitely and be retargeted. Now, I would say, fortunately, you may have read that this test of Skyfall blew up in northern Russia. But this new generation of weapons is on the way. So, again, hope for the best, but do not plan for the worst. For nuclear terrorism, I said we need to plan for the worst. But when it comes to nuclear weapons, there's no sensible medical plan. Things like, fallout shelters, medical facilities, these are not going to be effective in the face of a nuclear weapon, and certainly not in the face of a nuclear war. So again, the situation is prevention. We have to prevent these weapons from being used, and I think that physicians play an important role. So we're kind of, what we say, between a rock and a hard place. We have these nuclear risks. The more people that use nuclear energy, the more we have radioactive materials available to make weapons. But on the other hand, we're trapped with climate change. And this is obviously a either difficult or impossible balancing act. Now, one of the organizations that I belong to is called the Association of Atomic scientists. And the association has something that's called the doomsday clock. The doomsday clock is supposed to tell us how close are we to destruction of the earth. Now, you can see that, and so it's like a clock. You can see it was very close to destruction of the earth in 1953, in the middle of the Cold War, when the first hydrogen weapon was exploded. Now, at the decline of the Soviet Union, the clock hands moved back to, I think, 17 minutes. So things improved markedly. But you can see what's happened in 2018 and 2019. We are back to the same dangerous situation that we were in 1953. So the threat of a nuclear war and the threat of climate change has brought us to a very precarious situation that most people don't realize. What to do? Well, I suggest you have to keep calm and carry on. But I think as physicians, it's important that we play a major role in addressing these issues. You can't leave it to politicians. Physicians need to be involved. Now, I've gone through a huge amount of stuff in a very short period of time. I thank you for staying so long. If you want to know more, we've written a couple of books. This is the most recent one. You can get it on Amazon if you want to hear more about these issues. So the end is near. This is Bart Simpson. You may know him from The Simpsons, the television show. He happens to be a worker in a nuclear power facility, which is why I chose that. So thank you very much for your attention.
Thank you, Dr. Gale, for this extraordinary conference. And Dr. Daniel, we would like you to present Dr. Gale with the certificate on behalf of our academy. Congratulations, Dr. Gale. Em nome do presidente da Academia Nacional de Medicina, professor Jorge Alberto Costa e Silva, eu agradeço ao Dr. Rossano Fiorelli mais uma vez por estar representando aqui a comissão organizadora do Simpósio Internacional sobre pós-graduação na área cirúrgica e dou por encerrada a sessão de hoje. Muito obrigado a todos pela presença.